What Ohm's law says is that the current in a whatever, a wire, a light bulb, whatever it is, the current is directly proportional to the voltage when the current is held, when the temperature is held constant. Now, obviously, in any experiment, you have to hold lots of things constant. It's not just like the temperature, but the temperature is this like kind of special one because it will actually change as a result of you putting current. You just can't have current and not have an increase in temperature. So you can have objects that will follow Ohm's law, even if they're different temperatures, so long as the temperatures are relatively low. And that's what I think is happening in here. They're putting a small amount of current, so it won't cause the wires to heat up too much. And at low temperatures, most things do follow Ohm's law. As long as you don't allow the heating to get too dramatic, then the resistance stays pretty constant, and that's it. So question A says, does the wire obey Ohm's law? I would like to hear from someone, what do you think about this? What is the rationale behind whether these do or do not follow Ohm's law? So you have two wires, A and B, and I would like to hear an explanation. What is it that you would look at that would tell you that they are or they are not following Ohm's law?
You look at the slope.
What about the slope?
It's got to be linear,
Okay.
and the line itself has to like hit the origin.
So absolutely, that's the important thing. It doesn't matter what the slope is in terms of whether it's like 5 or 12 or 15. That doesn't determine whether you follow Ohm's law. What determines whether you follow Ohm's law is that that is a straight line, because it's impossible to have a direct proportion between I and V if that is not a straight line. That's going to have many, many different values for the current. Now, I'm not picking on Alexis because that was a great answer. I totally agree with that. But I do want to say one thing about this. The slope of the line is not the resistance. Okay, yes, the slope of the line will give you some indication of whether it's following Ohm's law or not because you're looking for whether it's straight or not. Okay, so to that extent, if you have a single slope with a straight line, yes, but the slope is nothing to do with the resistance in this. Now, what some people will say is that, well, that's true because resistance is V over I. So all I need to do to make this work out correctly is I just needed to reverse them. So it'll be V up here and I down here, and then the slope will be the resistance. Now, coincidentally, if an object does follow Ohm's law, that's true. The resistance will be the slope of the line. But the reason why that's true is because the line goes through the origin. It's because the line goes through the origin. Because if the line doesn't go through the origin, then the slope is not. Then the slope is absolutely not the resistance. Okay, so what I'm really trying to get across about this resistance calculation is, yes, it does look like R equals V over I, like that could be a slope. But is that how the slope of a line is calculated? Do you say M is equal to Y over X? No, it's not Y over X. It's the change in Y over the change in X. It's the rise over the run. But when you calculate the resistance, it's not a slope calculation. It's just a single value. It's the V at that particular point divided by the current that you got at that point. So it's not the slope that you're calculating. You are not calculating the slope when you calculate the resistance. And switching the variables so that V is on the vertical and I is on the horizontal, that doesn't change anything. You know, yes, that is V over I. But again, the equation for resistance is not delta V over delta I. It's V divided by I. It's the value at a single point. Now, the reason why it will be equal to the slope is because for objects that follow Ohm's law, they will go through the origin. So obviously, you can just always imagine that, like, what would be the difference if I picked one point and I did the division, or I picked that point and then subtracted out the 0? Well, obviously, if it's 0 in the V and 0 in the I. So it is true that for an object that follows Ohm's law, that if you do V versus I, the slope of that line would be the resistance. It would be the resistance. But I would say I would refrain from using the word slope when I talk about this. I wouldn't use the word slope. I would talk about whether it's curved or straight. Straight line, going through the origin, following Ohm's law, because that's what a direct proportion looks like. But it's kind of a subtle point, but they ask about it. They ask questions where it's obvious, it's clear. They're purposely, here's how I know they're purposely trying to do it. It doesn't make sense to put V on the vertical axis because V is not the independent variable. It's not like you take a fistful of electrons and jam them into a wire and then all of a sudden voltage appears. That's not how it works. You apply the voltage to the wire and that voltage supplies the energy to make the particles start moving. The current depends on the voltage, not the other way around. It doesn't make sense. There's no logical way in which you could start with the current and use the current to generate the voltage. It doesn't work like that in the real world. So it doesn't make sense for V to be on the vertical axis. But on the IB exam, I can think of probably at least 6 or 7 times I've seen on an IB exam where they did put V on the vertical axis. And I just don't know, like, I don't know if they're trying to be mean. They're just really trying to push you guys to the limits. I feel like that's a little unfair. But the reason why they do it is because they know that a lot of students make this misconception, or they have this misconception, that if you just make the graph V over I, then you can just calculate the slope and it'll give you the resistance, and you're missing what resistance is. It's not a slope calculation. It will never be a slope calculation. It is simply one value divided by another value, not the change in the value. That's a different thing. That is a different thing. It's just the state of its resistance at that moment. This has nothing to do with the change. Nothing's changing. Constant voltage, constant current. Nothing's changing, right? So that's a subtle thing, but kind of important. Now that I told you that, so as Alexis pointed out, these are following Ohm's law because they are straight lines and they go through the origin. Now the question will be, which of the two graphs corresponds to the higher temperature? Well, the one with the higher temperature is the one with the higher resistance. So that is kind of a subtle thing that maybe, I don't know, like I wonder what would you use as your guidance to answer this question if you don't recognize that? You're really, even though you're being asked which one of the two is at the higher temperature, the way you would answer the question is by figuring out who has the higher resistance. Because whoever has the higher resistance is extracting more energy from the charges as they pass by. Let me repeat that. What the resistance is going to tell you is who is extracting more energy as they pass by. So the more resistance I can put in there in front of that same current, the more energy that I can extract from that. So in this particular example, between A and B, and let's put this in the chat, you can just take your best guess. If you think you know the answer, then put the answer. If you're not sure, then at least guess, please. Is it A or B that has the higher resistance? Let's just take 20 seconds. Everybody throw into the chat. It's either A or B. A has the higher resistance or B has the higher resistance. Let's see what you guys think. So far, 3 people are going for B. I don't see anyone else putting anything in. See, what I would like is, and I think what we'll do in the future is I actually want to look into the poll thing because that's like a new thing that they added, and I'm sure some of your other teachers have used it. Only 5 people have responded. Thank you, Jasmine. Here's the thing now, it's ruined. Now it's ruined because everybody's going to start picking B. Right? I mean, there's very few people are going to go against the flow at this point because now you're not thinking about for yourself. Now you just want to don't look different than other people. So you don't need to keep putting any things in. That's fine. So the question is, how do we know? Well, obviously, if you think about, if you just let's just pick a point at some value. So let's say for this value of I. So where my cursor is right now, I'm going to slide over. There's the V for A, and there's the V for B. Well, obviously the V for B is much higher than the V was for A at the same current. This is like an important way. If you don't hold something constant, I don't know how you're going to figure it out. Like, it's just not going to work out. You need to hold something constant, and then you can make a fair comparison between the two wires. So if the resistance is V over I, and both of the wires, I'm looking at them at the same I, then it just comes down to whoever has more V. Or let's look at it the other way. Let's say I had a constant V. Okay, so I'm staying here on this part of the graph, and I'm sliding up. Here's the I that I get with that voltage on B, and then here's what I get with this guy on A. I get a much bigger current. So think about this. I have the same V on top, but on the bottom, A has a much bigger number. So therefore, the resistance is going to be lower. The resistance is going to be lower than it was for B. So I could show you how to do this using the slope, but I want to kind of actually avoid doing that. I don't want to show you how to do it using the slope. What I want you to do is figure out the V and I and do it in a way that allows you to make a fair comparison. I don't think on the IB exam they're going to ask you who has the higher temperature. What they're going to ask you is who has the higher resistance. And that is such a straightforward question if you just look at the equation. And that's something I really want to emphasize with you guys. Have the data book out. I mean, I really wish, unfortunately, Stephanie was the only one smart enough to realize like the data books were there in class when you guys came in. And unfortunately, she was in the third group. So by that time, the other two groups had already gone through. So the next time I go into school, I will be going to that packet of data booklets and I'll be dropping it off down at the what am I trying to say? The Park District doors. So if you wanted to go in and get it, oh, the computer's freezing, huh? Oh, that's interesting. Well, it's clearly me then, right? If it's more than one person not happening, and I'm not surprised by that. Let me check my Wi-Fi connection to see how strong. Yeah, it is a little weaker. That's so interesting. All right, let's switch to this guy. Thank you for letting me know that. I really appreciate that because I have a Wi-Fi extender and it wasn't connected to it. Somehow it must have reconnected to the directly to the Wi-Fi. Okay, hopefully that's going to improve it because that's a quite a bit stronger signal that I'm getting now. But let me just remind you guys, the video that I'm taking is going to be perfect. Like it will have no flaws, there won't be any lag or anything like that. The video will be perfect. So if you want to go back and you missed something, you just want to hear that little part again, you guys will be able to go back and do that. Okay, so hopefully that's going to improve things. All right, that's the only question I want to look at today. If you had questions about the lab, feel free to ask. I do feel like I wish I would have done the lab a little differently. I realize now it would have been really easy for you to just take screenshots of your setup so that I could see that you had done it correctly. So then that way I could know for sure that you had done it correctly. But it's fine, it's no big deal. The one thing that I did want to suggest to all of you, and I got to do it with one or two students, but I didn't get to do it with very many, is when you look at the last one, and where was that? What am I looking for? The lab paper, which is right. That's so weird. I don't know what I did with it. It's not here, it's not here, it's not there, it's not there, not there. There it is. Okay. So let me go through what I would have expected you to see. Okay. Obviously, when you get this one working, it's the light comes on and you see that there's a current in the ammeter. Okay. When you put two light bulbs, what you should have noticed is that the ammeter dropped, and I would suspect that these were dimmer. Okay, and the reason is because you've now added more resistance to the circuit. Okay, now the reason why we did this lab was to prepare for next week when we do the series and parallel lab, where we're going to be making circuits just like these, and I'll be giving you diagrams. So really, this activity was more about just learning how to use the software and learning how to connect ammeters, learning how to connect voltmeters and things like that. So we'll be doing another lab tomorrow for Ohm's law. And then I was going to do two kind of mini labs on wire properties, but I can't find a good simulator, so we're not going to do that lab. So let's just lower everyone's stress level, one less lab that we'll have to deal with. But I do want to do Ohm's law, and when we do Ohm's law, we'll add one more device called the voltmeter. So the ammeter, the ammeter will measure the current, and the voltmeter measures the voltage, but they are connected in different ways. And I really want to emphasize, and I'll go over that with you tomorrow. So this activity was kind of about where do you put the ammeter, how do you get that guy connected correctly so that it records the current, and how do you read circuit diagrams. What I would have expected you to find is that there was a difference between 2 and 3. So I would have expected 3 to have a much larger current, and I would have thought that the brightness of the bulbs was probably similar to number 1, while this one in number 2, it was much lower. The brightness was lower and the current was lower. Okay, now if you go to 4 and 5, where it's basically the same setup except for you've connected the batteries in different ways, when you connected it like number 4, I bet it was super bright and you had a lot of current. But when you connected it like number 5, the light bulb probably looked exactly the same as it did for number 1. And I'm sorry I didn't put the ammeter in there, but I would have put it right there. It would have been the same place where all the others are. You would not want to put it between the two batteries. You want it to be after the two batteries have come together. Now, if you have not already done this, I would just ask you to please try to do this. Go back to that one, set up number 5 again, okay? Get the current, see how things are working, look at the brightness of the bulb, and then disconnect one of the batteries. And if you have it connected correctly, what you should see is nothing happens. Nothing happens. The current does not change, and the brightness of the bulb is not impacted. Reconnect that battery, and then disconnect the second battery. Same thing. This is not how batteries are connected. And I would imagine you probably kind of know that. Batteries are connected end to end, lined up like in number 4, because you get more for doing that. Whereas for number 5, it doesn't seem like you're getting anything extra for it. Now, in reality, there is something different about it. There is something different about number 5 and number 1. Even though the current is the same, and even though the brightness of the bulb is the same, there is a difference in the circuits, but you can't see it with your eyes. And I'll explain that to you guys a little bit later once we get into the beginning of next week. We'll come back and we'll revisit this before we do the series in Parallel Lab. But so long as you recorded the ammeter reading and you told me how bright they are, you're done. And you just need to submit it. That's it. I don't want it to take a long time. If you're ever having problems, let me know, and I will help you to get the thing sorted out. But I want to get this thing done and move on so I can give you the grade for it, and we can all move on. It's really not about learning about science so much as it just getting used to the diagrams and the way the equipment works, so that on Thursday, when we do the next lab, I don't have to explain the ammeter again. The ammeter should be connected in series or be connected directly to the object that you want to know the current for. So if I want to know the current for X, I would just put the ammeter right there. I would connect it right next to X. But that ammeter should be in the circuit. Okay, it should be in the circuit. It should be part of the circuit. Now the simulator that we're using actually allows you to use this some kind of weird ammeter. I've never seen an ammeter like that. I don't think it actually exists, where you could just put it on one spot and it would tell you the current at that spot. That's not a real thing. We would never be able to do that in the real world. The way ammeters work is they must be connected in the circuit, and they work very much like a turnstile. You know, you guys might not realize it, but when you go through a turnstile, right, these things that when you have to go into like Great America or something like that, and they put this like thing that rotates in front of you, it's counting people. That's how they know how many people came in. You know, you can't base on the number of tickets sold. That doesn't mean that the people showed up. So they count the people as they're going in. That's a counter. Every time it rotates, one click, it counts one person. Some of them you can actually see it. If you look on the end of it, you can actually see the counter. It actually shows you how many people have been counted. So that's what the ammeter is doing. It is, again, can't stress this enough, it's counting how many charges are moving past per second. That might be because there's so many charges, or it might be because there's a small number of charges, but they're moving very quickly. And that's why so many charges are moving by. So the ammeter is simply a counter. It counts how many charges are going by per second. That's it. And in order to do that, it's got to be in the circuit, sort of like the way the turnstile works at the L or at Great America. All right, what time are we at? 12:36. All right, good. That leaves about 20 minutes left to go to independent study. I will let you know in about 10 minutes that if you want to go to completely asynchronous, you could do that. But in the meantime, please stay in the class for about the next 10 minutes or so. Let me stop my recording.